VF lens, enhancing visual perception of visually impaired users via adversarial learning with visual field attention. According to the World Health Organization, there are at least 217 million people worldwide have varying levels of vision impairment. The people in this substantial group, representing potential VR users, often are associated with particular visual field impairments at varying levels. Visual field impairment, also known as visual field loss, is a condition characterized by reduced light sensitivity in the visual field. Individuals with visual field impairment may experience a range of symptoms, from decreases in light perception to complete vision loss, based on the severity and location of the impairment. Our research aims to enable visually impaired users with depressed light sensitivity to perceive visual information in a manner that closely approximates the visual experience of users with normal vision. A visual field map is a specialized instrument used to measure an individual's visual field condition. This figure shows an example of measured visual field parameters and the corresponding visualized visual field map. As illustrated in this figure, visually impaired users may encounter areas in their visual field that appear dark or may even become completely invisible when viewing natural images. Given the visual field map, the impaired perception of the user can be simulated by using the user's visual field parameters. In this work, we propose VF lens that bridges the gap between visually impaired users and the VR world. VF lens is an adversarial learning-based image enhancement model that aims at empowering visually impaired users to perceive visual information similar to users with normal vision. In VF lens, a hyperimage is generated to overcompensate for brightness to match the user's visual field impairment. The generated hyperimage is displayed to the user through a VR head-mounted display. The user's actual perception is regressed from the hyperimage, aiming to approximate the targeted normal vision image determined by the discriminator. Through adversarial learning, VF lens presents an innovative method that can potentially address a broad range of visual impairments, not relying on the transparency or reversibility constraints inherent in various visual impairment simulators. This is VF lens's network structure. Blind spots represent imperceptible areas, and enhancing them is unnecessary. Therefore, in pre-processing, we adjust the parameters of these areas and exclude them from the computation process. We transfer the simulated impaired perception image to the VF significance attention module to extract attention, and concatenate it with the original image as input to the generator of VF lens. The generator of VF lens generates a hyperimage to overcompensate for brightness to match the user's visual field parameters. Then the overcompensated hyperimage undergoes a regression process using the visual field parameters to predict the actual perception of the visually impaired user. The discriminator's role is then to compare the regressed perception with the original image to ascertain their similarity. After adversarial training, the generator is expected to yield a hyperimage that, when regressed with the user's visual field parameters, closely resembles the original image. As demonstrated above, VF lens, with its adversarial learning capabilities, has the potential to address a wide range of visual impairments for image enhancement, even if the visual impairment simulator is irreversible. We next present our experimental results and findings. Original image. Simulated impaired perception. Hyperimage. Simulated regressed perception. Our evaluation encompasses both objective and subjective assessments, utilizing a combination of traditional metrics and specifically tailored metrics designed for our task. In the objective evaluation, we extended state-of-the-art image enhancement methods to incorporate visual field parameters, enabling fair comparisons with VF lens. In the subjective evaluation, we engaged a total of 50 participants to assess the quality of images or videos that had been processed by VF lens. In the objective evaluation, we conducted a comparative experiment for image enhancement utilizing both traditional metrics and tailored metrics. We extended the benchmark image enhancement methods to incorporate visual field parameters, similar to VF lens, to enable fair comparisons with VF lens. As demonstrated in the table, VF lens consistently exhibits significantly superior performance compared to all benchmark methods by a substantial margin. Remarkably, VF lens achieves PSNR gains ranging from 2.34 decibels to 6.54 decibels compared to the benchmark methods across various levels of visual field impairments. We also conducted an ablation study to evaluate the effects of the attention mechanisms we proposed within VF lens and to determine their optimal configurations. The outcomes for these configurations are detailed in the provided tables. These results highlight the substantial impact of the proposed attention mechanisms on the performance of VF lens. Here we show sample images enhanced by VF lens in comparison to the benchmark methods. The results demonstrate that VF lens excels in providing a more natural image perception that is closer to the original image, particularly in cases of severe visual field impairment. In the subjective evaluation, we recruited a total of 50 participants, consisting of 20 visually impaired participants and another extra 30 virtual patients with simulated visual field impairments, following the existing experiment protocol. All participants used the Oculus Quest 2 head-mounted display to view the images and videos during the evaluation process. For the 20 visually impaired participants, we initially conducted visual acuity tests using their personalized Landolt-C visual acuity chart to assess their visual acuity levels. Upon statistical analysis of the testing scores, we observed significant differences, p equals 0.029, in the performance of the participants when using VF lens compared to when it was not utilized. Then the visually impaired participants proceeded to an adapted VF14 questionnaire using 16 testing images encompassing 6 distinct living scenarios, including reading text, interpreting road signs, recognizing people, daytime travel, nighttime travel, and stair climbing. The analysis reveals a statistically significant difference, p equals 0.02, between the use of VF lens and its absence. These results underscore the effectiveness of VF lens in mitigating visual impairment challenges among visually impaired users during daily activities within a VR environment. Furthermore, we have conducted qualitative interviews with 16 out of the 20 visually impaired participants to gather insights on their experience, limitations, and suggested future development of VF lens. The results are presented in the supplementary material. To address the shortage and difficulty in recruiting visually impaired participants, we recruited another additional 30 participants to act as virtual patients with simulated visual field impairment, following the existing experiment protocol. We compared VF lens with benchmark methods by evaluating the perceived video quality in VR using the mean opinion scores, MOS, rated by the virtual patients. The results show that VF lens achieved an average MOS of 3.8, significantly surpassing the average MOS of 1.8 to 3.4 obtained by the benchmark methods. The above results are consistent to our previous objective and subjective evaluation results. In conclusion, we propose VF lens, a novel and promising approach designed to improve the visual perception of visually impaired users in VR to approximate that of users with normal vision, serving as a virtual lens connecting the visually impaired users and the VR world. For more details on our VF lens model, comprehensive experimental results, as well as discussions on limitations and further insights, Please refer to our paper and supplementary material for a more in-depth understanding.